Hello, everyone. I'm Caslin Fields, and I am your track host today. For the last session of the day, congratulations to all of you for making it this far. Woo! You are all the real MVPs. So we are here today for the last session of the performance track, Staying in Tune, Optimize Kubernetes for Stability and Utilization, by Randy Johnson and Koushik Radhakrishnan from VMware. I'm here to remind you there will be a feedback form available after the session. Our speakers and we at the CNCF would really appreciate it if you would give us your feedback. I know they're really hard to remember to do, but we would very much appreciate it. And I will be running around the microphone for Q&A at the end of the session. Now, Randy and Koushik, take us away.
Thank you so much for being here. It's the last session, like we mentioned. We're going to talk about staying in tune, optimizing your Kubernetes clusters for stability and utilization. It's a very overlooked topic, and I think whatever we learned in field engineering, as a field engineer at VMware, we've tried to put it in this topic, and hopefully you'll take it back and implement and tune your clusters accordingly. So I'm Koushik Radhakrishnan.
And I'm Randy Johnson.
So let's talk about this. I mean, Kubernetes, it has potential. It's gone way beyond potential right now. I think the first step to have this increase beyond its potential is the declarative API. I think we all know like API is like the first-class citizen. It's all about software interfacing with software. And then the next important aspect of this is the control loop aspect. I mean, it's the self-healing side of things, autonomously converging on building blocks. You're having resiliency at the app and infra layers. So these are kind of the two main primitives. But for our talk, we're going to look at the bin packing aspect, which is very important, and we'll be discussing a lot about limits and requests. It's all about determining where's the best pod placement. It's approximation with like performance guarantee, like we mentioned. So this is what we're going to be looking at in our talk. So we have to break these invisible walls, right? I think we always have these default parameters that we set up, and we tune our clusters that we go through. But we need to break these walls and optimize our clusters accordingly. I think we don't know where that ceiling is or where the invisible wall is, and we have to look at these clusters and then take these default values that's been set up and then kind of change them. So for the goals on this talk is the two main things that we're trying to look at. Like we mentioned, it's stability and utilization. They always seem to be at odds with each other, but we believe that with a solid understanding of these stability and utilization, we can achieve both, which is always good for your business as well. So what are the challenges? Let's look at the challenges that we have. I mean, Kubernetes isn't configured for our app. I mean, it's resources, burst, priority. You're looking at a lot of these aspects for when you're having your app getting deployed onto your Kubernetes cluster. Configuration is also very important. And I mean, when we have your app deployed on your Kubernetes cluster, your utilization is increasing. The behavior of clusters become even more complicated. In our talk, we'll go into depth about how these behaviors affect us or affect these clusters. And like I said, I mean, the app, we have these apps getting configured, the utilization increases. Whenever utilization increases, we're always leading into disruptions. There's expected disruptions that you can see, and there's unexpected disruptions that you're probably not going to encounter. I mean, you're going to encounter it, but you're not aware of. So how can we maintain stability when we have these disruptions? So we always believe that in this cloud model that we talk about, the target is always moving. There is no like an as-is state. You're getting to a to-be state where you're the target is always in a moving state. Your app requirements change. The underlying infrastructure or the hardware is changing. The only constant for all of us, which is why we are all here, the Kubernetes is constant. It binds the app and hardware. And these are the challenges that kind of like you're going to fix it with a moving target that we're talking about. You're going to be optimizing your app based on that target. What can we do about it? Two things, the limits and requests. We're looking at scheduling, overcommitting, and eviction. Then you're also going to look at allocatable capacity, and we're going to look at why that is important. In the allocatable capacity, you're looking at defaults, the eviction threshold, why kube and system reserved components are all important for you, and how you should look at tuning these parameters.
All right, thanks. All right, so we're going to start with a simple example and introduce limits and requests and go over some of the problems that those solve. And then we're going to tie that back to some of these other behaviors that are really important within Kubernetes as we approach utilization. So here's our example node, and it's a really simple node. Right now it just has one replica of pod A deployed to it. And there's a couple problems with this. The first of which is that when the scheduler placed this pod on this node, it didn't do that based on any sort of information about the resources that it needs. And another problem that's even bigger than that is that the resource consumption of this pod is unbounded. So this pod is free to consume all of the available resources on this node. So when we deploy a second replica of this pod, notice that the CPU utilization is split evenly. So this is because CPU is a compressible resource. And that means that when the CPU is fully exhausted, each of its consumers will be throttled, so they'll be slowed down. But memory, on the other hand, is incompressible. So when we run out of memory, it's a really big problem, and we can't compress it in the same way that we could CPU. So at this point, there's a couple things that can happen. Ideally, one of these pods would be evicted. But since the node is fully utilized, it's also possible that the eviction process doesn't occur fast enough, or that it doesn't occur at all. So that's problematic because at that point, you would be reliant on the node's out-of-memory killer. And we're not going to go into the details on that, but basically, one thing that's possible is that the out-of-memory killer kills Docker, and if Docker goes down, all of the containers on this node will go down as well. And there is a way to fix that, and there are ways to mitigate against this, and we'll be getting into details on those. But just to recap on the two types of resources, CPU, not a huge deal if we run out of it because it'll be throttled. It's a compressible resource. But memory, on the other hand, is problematic if we run out of it. You can think of memory as being incompressible like water. So if you try and compress it, you're going to have a bad time. All right, so what do we do about this? The first thing we should do is set up limits. And a limit is just a way to specify an upper bound on resource consumption. So for CPU, which is a compressible resource, the limit is going to be the point at which CPU is throttled. It's going to be the point at which this container is slowed down. Memory, on the other hand, because it is incompressible, when memory utilization reaches its limit, this container is going to be killed and restarted according to its restart policy. Likewise, similar to specifying the upper bound on containers, we can also specify a lower bound. And we do this by setting a request. And we illustrate this with the dark green squares. So it turns out that even though these are really simple ideas, just specifying an upper bound and lower bound on containers, these have a huge effect on the overall behavior of our cluster. So limits and requests lay the groundwork for scheduling. It affects how well informed the scheduler is to make a good decision on pod placement. It affects overcommit. And overcommit is the process of assigning more resources to containers than the node actually has available. They affect eviction. And eviction is the process of kicking pods out of a node to reclaim resources and maintain stability. These are the three main processes that affect stability and utilization within a cluster. And if we want to achieve both stability and utilization, we need to be aware of and understand these ideas. All right, so back to scheduling. So in Kubernetes, the scheduler filters nodes based on requests. And based on the request here, it looks like another pod could fit on this node. But based on its utilization and our previous example, we know that another pod would not be successful on this node. So what can we do about this? One way that we can solve this issue is by setting the request equal to the limit, or at least closer to the limit. Because the scheduler filters nodes based on requests, it's going to compare this pod's request to the remaining allocatable capacity on this node. And we'll get into allocatable a little bit later. But basically, we're solving this problem by informing the scheduler that a second replica of this pod would not fit on the first node. And this seems a little odd. Why might scheduling be implemented this way? So one side effect of this is that this allows us to implicitly manage overcommit ourselves. So overcommit, again, is the process of assigning more of a resource to pods than the node actually has available. And because the scheduler only considers requests, not utilization or limits, we implicitly configure this with the difference between limits and requests. And whether or not overcommit is a good idea for your app is really up to you. But at a high level, without overcommit, which can be achieved by setting requests equal to limits, your utilization will be a little bit lower. You would never run out of resources, but you're basically buying stability at the expense of utilization. With overcommit, if you allow requests to be less than limits, you could achieve higher utilization, you might run out of resources, and you're basically buying utilization at the expense of stability. So quality of service is a class that's assigned to pods based on their requests relative to limits. And in each of our previous examples, we've had 3 different configurations of request relative to limit. So if you have no limits or requests, that would correspond to a best effort quality of service, and this is the lowest quality of service. If you have requests set less than limits, that would correspond to a burstable quality of service. This is the middle quality of service. And then if you set your requests equal to your limits, then that would be a guaranteed quality of service. And guaranteed means that the pod would never be evicted because of another pod's resource consumption. So let's go over an example of eviction. Again, eviction is the process of kicking pods off of a node in order to reclaim resources and maintain stability. So each of the letters here corresponds to a pod consuming a varying amount of memory relative to its request and limit. And we're going to use memory here as an example because, as we've mentioned earlier, running out of memory is the biggest risk to stability. This animation shows the order in which pods from the previous slide are prioritized for eviction. So notice that the first 4 pods all have a quality of service of best effort. And the 3rd and 4th pods that are evicted actually have the same priority. So when this happens, the quality of service is equivalent and the priority, then they're ranked by the utilization. And now with the burstable pods, because we have a request and that we can compare the utilization to, even though these are the same priority, we compare the utilization relative to the request. And then last would be a guaranteed pod. And again, guaranteed pods will never be evicted because of another pod's resource consumption. But if system daemons were to burst, then in that case, they would be evicted. And in that sense, you can also think of system daemons as having a guaranteed quality of service. So by default, limits and requests are optional. And this is kind of because there's not really a sensible default for these values. It's entirely up to us to set these. And even though there's no error or even a warning if we deploy a pod without limits and requests, they're still incredibly important. So the way that we enforce these and force defaults to exist on pods is by setting up a limit range object. And a limit range object will allow you to set a minimum, maximum, a ratio of limit to request or default values. So when you set up this object, the limit ranger admission controller will enforce all of these rules on pods as they're deployed to your cluster. And then we can also set up quotas at the namespace level, and you would use a resource quota object to do so. All right, now we're going to get into allocatable. And this is a really important concept to understand. And I think it's especially important that we as consumers of Kubernetes think of nodes in terms of allocatable capacity and not just total capacity. So this is important because it's how the scheduler filters nodes. It looks at the remaining allocatable capacity for a resource and compares that to a pod's request. Allocatable is also the buffer in which pod utilization can burst. And we can also, and the edge of allocatable, where allocatable ends, is one of the thresholds that can trigger pod eviction or throttling, depending on the type of resource. And we can also think of allocatable more broadly as one of the main tunables for adjusting stability versus utilization. So you can imagine to tune for stability, we could decrease allocatable. And when we do this, this would result in less allocatable capacity for the scheduler to place pods. There would be less of a buffer for pods to burst, and there would be a greater buffer between the point at which eviction begins and the total capacity of the node. And this would make it less likely for daemons to experience resource contention. So likewise, the opposite is always true. If we wanted to tune for utilization, we could increase allocatable. And again, this would just give more capacity for the scheduler to place pods, more of a buffer for pods to burst, and there would be a smaller buffer between the eviction threshold and the actual capacity of the node. And this would, of course, make it a little bit more likely for resource contention to occur. So overall, as allocatable shrinks, we're tuning for stability, and as it increases, we're tuning for utilization. So let's talk about what allocatable constraints are, because that's what allows us to tune allocatable. All right, so to start, let's take a step back and take another look at what nodes actually look like on a newly installed cluster. So by default, pods and daemons consume resources, and we've kind of been glossing over this fact up until this point. But now everything on the left is going to represent utilization of pods and daemons. And everything on the right is going to represent allocatable constraints. So notice the only thing that we have on the right is an eviction threshold for memory. And this threshold applies to the total utilization of pods and daemons. And when the total utilization hits this point, that's when eviction begins. So one problem with this is that pods and daemons are actually competing for resources. The scheduler does not take into account resource consumption of daemons. So the way that we can mitigate this is by setting kube and system reserved, which are actually disabled by default. So kube reserved is a way to set aside resources for Kubernetes-related daemons like the kubelet and Docker. System reserved is for everything else on the node. And when we set these up, these are factored into allocatable constraints. And as that increases, allocatable decreases, like we were discussing before. So this is how we take into account daemon resource consumption and prevent pods and daemons from competing for the same resources. And again, there's not really a default for this either, because there's not really a sensible default to set. Kubernetes is unaware of the underlying hardware and our app requirements. So again, this is something that's really up to us to set up and tune. And just to recap for CPU, the scheduler uses allocatable to schedule based on CPU requests. Allocatable is the buffer in which CPU utilization can burst. And when utilization exceeds allocatable, pods will be throttled to prevent contention with daemons. Similar story for memory and ephemeral storage. The only difference here is that we include the eviction threshold in node allocatable constraints. And quick side note on that, eviction only applies to memory and ephemeral storage, I believe, right now. So I don't think you can currently trigger eviction based on pod CPU utilization. Again, so the edge of allocatable is a threshold for eviction, not throttling, because this is a incompressible resource. And one important note here is that we now have two thresholds for eviction. One is the same one that we discussed earlier, which is triggered by the total consumption of pods and nodes. That's the eviction threshold on the far right. And another is the edge of allocatable, and this one is triggered by the consumption of pods. And although we use CPU, memory, and ephemeral storage as examples, those are just what's currently supported and documented. But it's also important to note that the concept of allocatable could potentially be generalized beyond these types of resources. And just keep this in mind, and we could extend this API to someday account for any type of resource that we want. maybe GPUs, for example. All right, so this is a lot of new information. What are we supposed to do with it? So there's some key questions that we can ask ourselves with this to inform how we set up our cluster. The first of which is our scheduler prepared to make informed decisions? So remember, by default, limits and requests are optional. The way to enforce that is by setting up a limit range object. Once we're using limits and requests, one of the most important things to consider is utilization relative to request. And this cuts both ways. When working with customers, we found that if, for example, app teams consistently overestimate how much of a resource their app needs, the scheduler will think that the cluster is full because it's comparing the pod request to the allocatable capacity of each node. But if you look at actual utilization, then it's going to be hovering around like 5 to 10%. But also the opposite is also true. So if utilization is considerably higher than your requests, you'll be consistently running up against limits in the best case, because then that pod will be throttled, and the blast radius of that will be limited to one pod. But also, it could run up against eviction thresholds, which would cause instability at the app layer. And then the worst possible scenario is if eviction isn't fast enough, or it fails, and then you're reliant on the node's out-of-memory killer. Is overcommit configured properly? So if our limits are too high, this could result in eviction occurring too frequently, and that's because the utilization would be running up against eviction thresholds. If our limits are too low, this could result in containers restarting in the case of memory, for example, because those containers would be killed and restarted, or throttling in the case of CPU. And how close are we to triggering eviction? So this question is a little bit more nuanced than just looking at memory. And available memory is important, but that tells us when the entire node is at risk. So because we understand these eviction thresholds and these values are well defined and known ahead of time, we can be a little bit more proactive in our approach to monitoring. So by knowing exactly when eviction is going to occur, we know when instability at the app level is going to occur, not just instability at the infrastructure level. So again, these two eviction thresholds, this one is for the allocatable capacity of pods, and this one is for the eviction threshold. This is the first one that we went over. And monitoring these two eviction thresholds can be really powerful because it informs our decision-making process moving forward for how to tune our clusters. But we also know the cause of eviction, and that's what allows us to tune it. So we can build upon this further and ask ourselves, all right, what if we frequently encounter eviction caused by utilizing allocatable? Well, in that case, we would know that we need to tune our limits and requests to adjust our overcommit. And if we know that we are frequently encountering eviction caused by crossing the eviction threshold, we know that we need to tune kube and system reserved. So this is because we haven't set aside enough resources for our system daemons. And I know it's late in the day and I'm throwing a little bit of math at you, but this will be easy, I promise. So in all of our examples so far, we've been considering allocatable at the node level. And it turns out we can generalize this a little bit further and think about the allocatable capacity of our cluster. So this can help us be a little bit more proactive in how we think about failover, for example. So imagine if you have two nodes. If neither node goes above 50% utilization, you know that one node failing wouldn't be a huge deal because those workloads could be rescheduled on the other node. And there would be a temporary disruption, of course, but those workloads would at least be able to be rescheduled. And disclaimer on this idea, because this does assume that nodes are the same size, and it doesn't account for things like affinity, taints, and tolerations. So scheduling is a bit more complicated than this. But the point is, if these values are well-defined and known ahead of time, why not plug them into monitoring tools to help us be a little bit more proactive? And this is one example of how we might do that. And I forgot to advance the slides, but we could generalize this for an arbitrary number of failures. So imagine if you had 2 nodes and 1 failure, this would be 50% as your upper bound for utilization. Or if you had 10 nodes and 1 failure, this would be, your upper bound for utilization would be 90%. And because our node allocatable constraints are well-defined and known ahead of time, we can take that into account as well and be even more precise in our estimate. These are some of the defaults that we think it's really important to be aware of. So eviction hard, this is the default eviction threshold that we talked about earlier. Housekeeping interval is the interval in which kubelet takes a snapshot of resource utilization on the node. So the kubelet doesn't actually have a real-time understanding of resource consumption. Eviction pressure transition period is a mouthful, but it is also how long it takes for a node to be able to schedule pods after an eviction threshold is met. So I think that's a really important one to be aware of because it's 5 minutes. So taking these 3 into consideration, here's what a worst-case scenario might look like. And I know this from experience. So let's say our workload consumes more than 100 MB faster than 10 seconds. The eviction process doesn't begin fast enough, or maybe it doesn't happen fast at all. Now we're reliant on the node's out-of-memory killer to save us. And in the worst case, Docker is killed by the out-of-memory handler, and every container on the node is taken down. In the best case, we can reclaim resources on the node, and the node is stable again. But we can't schedule anything on that node for 5 minutes. So in the meantime, as these 5 minutes are ticking down, pressure on the remaining nodes is increased due to workloads being rescheduled on those nodes. And again, this raises the possibility of this scenario occurring on every node, which could potentially result in a cascading failure throughout the cluster. So I bring this up because at the very least, you might want to increase the eviction threshold. The default there is only 100 MB, and decrease the eviction pressure transition period, unless your app can tolerate a 5-minute downtime. And for Docker, quick note on this. So I've got implied defaults up here. So if you don't pass any flags in, the implied defaults are effectively what is passed in. But I included the flags up here in case you wanted to add these to kubelet and tweak them. But again, if you don't do anything, this is what they would look like. Before we talk about Docker, we've got flags to consider. So kube reserved and system reserved, we talked about these earlier. These are how you set aside system resources for daemons. And eviction soft. This one is similar to the other eviction threshold that we talked about, but this one is not considered, it's not accounted for in allocatable constraints, so it will not affect your allocatable capacity. But once this threshold is triggered, there's a timer that starts ticking down, and when that timer hits 0, if the eviction threshold is still being violated, then eviction will begin. So it's kind of a nicer eviction threshold. And the grace period below is how you would tune that timer that we talked about. And onto Docker. So as we were saying earlier, by default, when Docker terminates, it'll kill all of the containers on that node. And there is a feature to mitigate against this. It's called live restore. Again, implied default, if you don't do anything, this is what it looks like. So the default value for this is false. But if you do want to take advantage of that feature, you'd have to set this flag to true.
Well, that brings us to the summary. Again, we looked at a lot of things. One is the limits and requests and allocatable capacity as well. In limits and requests, we went to scheduling, the overcommit, eviction, and we also looked in the allocatable capacity, defaults, eviction threshold, and kube and system, and how you can go about tuning those parameters for your own clusters. Again, please keep in mind, we've done this for a lot of customers. Every cluster is different. Every app that you deploy in a cluster is different. You'd have your own environments to think about. But if you have more questions to ask us, please feel free to reach out to us. And hopefully this was insightful in how you can optimize your clusters. Well, thank you for coming, and hopefully everybody. I'm sorry. Yeah. Questions?
Questions? I saw this hand over here first, so I'll run over here. Don't forget to do your feedback forms. Also, I will not remember, probably, clearly.
Thanks for the presentation. I did remember reading somewhere that we should avoid setting CPU limits because of something with the CFS, the Compute Fair Scheduler. Do you know if that's still the case?
I can answer that.
Oh, great.
I fixed it.
Woo!
If you're interested in that, there is a talk about throttling. It's called Throttling New Developments and Application Performance with CPU Limits. Yeah, I should have had a better title. But the end result is there's 3 kernel commits you need to make it useful. Again, so it's actually fixed. Just upgrade your kernels.
Cool.
Next question. I saw your hand earlier, so I will come to you first.
So first of all, thanks. This is great information that everyone really needs to know, even if they don't know they need to know it yet. You focused mainly on the node. What do you find as the best way to put some of those quotas on, say, a namespace so that you don't have like capacity creep as they keep adding things, looking at more of like a multi-tenant cluster?
Yeah, so the resource quota object that we brought up is namespaced, so that would apply at the namespace level. Is that what you're getting at?
No, yes, you would use that. More the question is what are the tools to look to try to come up with what that quota for the namespace should be based on all the pods running in that namespace? Mm-hmm. Does that make sense?
Okay. Yeah, so...
Depends. Sorry, no, go ahead.
Yeah, so to approach that, I would probably start with just monitoring tools to figure out what our requests and limits should be for the app so that we know what appropriate settings are for that. And then I'd say the quota is really just going to be based on that. What do you think is appropriate for the apps in that namespace?
Again, it depends for every environment that we work with, but that's the tools that we have relied on so far to just set quotas for specific things.
Okay, so you're saying just like kind of add up all the limits and add up all the requests and kind of set that as the quota?
Yeah, it's a little bit of a guessing game for what the right value is, but you definitely have to have a feedback loop that involves monitoring tools. Mm-hmm. So yeah, deploy your app, use monitoring tools, figure out what appropriate values are, and then just kind of iterate on that.
It's always a constant, like we discussed about the moving target. It's always a moving target in what you're trying to do. So you'd have to get it done in your testing cluster and then see what your app teams are thinking about and then set your limits accordingly.
Yeah, essentially what we've been doing is kind of what you're describing, looking at Prometheus for like the last week and looking at the historical data and try to guess what that is. I was just wondering if there was maybe a tool out there that would help with that. I don't think there is. I haven't seen one. I just was wondering if you guys...
So this might not be answering your question very well either, but one tool to check out is Vertical Pod Autoscaler. It can help automate the process of setting limits and requests. But as far as what an appropriate quota should be for the namespace, I don't know of any tools for that.
While I was in the floor, I did see somebody called Densify who was kind of doing the same thing about monitoring those specific and then able to tool. So you could probably check that out. But we've relied mostly on the CNCF projects and monitoring tools to get our things done.
Okay, thank you.
Okay, I'll do this one first, and I'll come around the room to you.
I'm curious if you have any practical experience with interactions between pods that have pre-stop hooks and how that plays into like soft eviction and hard eviction limits. So let me give you kind of an example. If I've got an application that's got a long-running pre-stop hook, and the node goes into a soft memory condition and breaches that threshold, but doesn't, and stays there, and then other pods continue to consume resources as that hook terminates. And if you then breach the hard eviction limit after that, how the sequence of events would play out if you guys ever encountered that in the work that you've done. I have a general sense of how those interact, but I'm curious if you ever ran into something like that.
So it's not something that I've encountered myself, but I would imagine that it sounds like it might be a good use case for the soft eviction threshold. I would imagine if you had a brief increase in utilization, and then maybe you could adjust that grace period to account for that. Might be something to think about. Yeah, I hope that helps answer the question, but overall, no, it's not something that I've encountered myself.
So when I was reading up on how Kubernetes handled limits and requests, one of the things I read, source is probably irrelevant, but anyways, it sounded reasonable, so I made an assumption that was true, is that when you set a limit and the process wants to go beyond that, if there is free CPU cycles, Kubernetes will allow it to use those, so it'll allow it to exceed the limit. However, I've since seen several cases where Kubernetes actually throttled on the limit even when CPU was idle. So what is the intended function and behavior? How should Kubernetes handle that?
So I believe it throttles at the limit.
So it's a hard limit even if there's free CPU cycles?
I'm not totally sure. It sounds like this person has worked on this, but
So yes, at the limit, it's going to throttle because it's going to use secret CFS quota.
Mm-hmm.
So the kernel itself is going to not schedule that pod any longer until the next period, which is by default 100 milliseconds. Requests can burst up to the limit, but the limit is a actual limit now.
It's a hard roof. Yeah, that's what I observed too, which caught me by surprise, but now that I know that I can accommodate it.
I believe this will be our last question.
Hey, so thanks for giving this talk. If you are on EKS, you should be aware that the newest AMI they just released on Tuesday actually sets the cube reserved and the daemon reserved by default. This actually caused a fire for us because cluster autoscaler, which will add more nodes to your ASG, doesn't take into account if you have cube reserved actually set. So pods would try to be scheduled onto these nodes. It didn't do the math, thought that there was actually a larger than normal amount of memory, spun up another node, and then that failed. It said, oh, I just need another node, added another node, and you can see where this goes from here. So yeah, just be aware, by default, it's not set unless you're using the EKS AMI. But thanks for giving this talk. This was great. Thank you.
Thank you.